Hello, everyone, and welcome to the SILCS version 2025 release webinar. We are excited to have you here with us today as we introduce the latest advancements in our SILCS technology. I'm Abhishek, your host and one of today's presenters. Joining me are Oliver and Oscar, who will be walking us through the key updates and case studies. Later, we will have Q&A where uh, Alex Mackerel and Olgun Guvench, our co-founders, will also join the session. Before we begin, let's take a brief moment to ensure everyone has joined. And while we wait, I'm going to launch a quick poll to see how everybody is. How well do you know SILC's technology? So let's try to answer that for a second while we wait for other people to join. Okay, looks like we have a few people who are new to SILCS. That's great. We'll have a short introduction to the SILCS methodology in our slides today. So while people are responding, a few housekeeping notes. The webinar will run for about 55-60 minutes with a Q&A session at the end. You can submit your questions anytime in the chat and we'll address them during the Q&A section. The session is being recorded, so we will share the recording and with all the registrants afterwards. So to give you an overview, at SILCS Bio, our mission is to provide innovative computational tools to enhance flexibility in drug discovery workflows, improve usability, and deliver accuracy in molecular modeling. With SILCS version 2025, we are bringing major enhancements to make the platform even more powerful and user-friendly. So let's get started. Hello, everyone. Welcome again to the SILCS version 2025 release webinar. Let's get started. Today, we will be going over these topics. For those who are new to SILCS, we will briefly introduce the SILCS method. Then we will take you through some exciting new features we are releasing in version 2025, followed by a case study using the small molecule suite. Lastly, we will talk about what's in the development stage and end the webinar with a Q&A session. Let's begin with an introduction to SILCS. The fundamental idea behind SILCS, which stands for Site Identification by Ligand Competitive Saturation, is to use simple chemical solutes to map the functional group affinity of the entire protein. The probe molecules, along with water molecules, compete with each other to occupy the most favorable interaction sites on the protein surface. We extract this information, analyze, and process it to generate a pre-computed ensemble of affinity maps, which we call frag maps.
We will show how this one pre-computed ensemble can then be used for various tasks in drug design campaign, such as site identification, virtual screening, hit identification, hit to lead, and lead optimization. Here is what undergoes in a silk simulation. We start with a protein and immerse it in a box with SILCS probes. Note that there is no ligand present in this case. 10 systems of the solvated target protein with scrambled side chains are generated as starting structures for 10 independent runs. We then run each of the 10 systems for 100 nanoseconds of MD simulation. After 1 nanosecond of MD simulation, we introduce an enhanced grand canonical Monte Carlo, that is GCMC simulation, for 100K steps before resuming the rest next MD simulation. Here, the MD simulations allow for conformational sampling of the protein as well as the probes and waters. And the GCMC simulation allows for sampling of probes in the deep pockets. The information from this huge calculation is then processed to generate the frag maps as shown on the right hand side here. To do that, we divide the full 3D space into tiny cubic voxels and calculate the probability of each probe occupying the voxel. Now here is a representation of what we find in the presence of a protein. The probability of the probe molecule occupying a given voxel is driven by its favorable and unfavorable interactions with the protein. There are regions with higher and lower probabilities than the probability of probes interacting with each other in the absence of the protein. And importantly, there are regions with no probability. All these probabilities are then normalized with the bulk solution probabilities and Boltzmann transformed to get a grid free energy at each cubic voxel. This is done for all types of atoms in the set of probe molecules, giving us the final frag maps. Now, we can visualize these frag maps in reference to our starting structure, visualizing different frag maps that represent apolar, hydrogen bond donor, hydrogen bond acceptor, positively and negatively charged regions can be quickly analyzed for qualitative assessment of your target. Additionally, different GFE levels allow for regions that will bind the specific chemical class most tightly to be identified. Unfavorable regions may also be identified. Now, to use frag maps in a quantitative way, we first take the ligand pose and overlay in the field of frag maps. We then take each ligand atom and assign a frag map type to it. Then, based on the location of the atom and the grid free energy at that location, we can then get an atomic contribution to the ligand's energetic favorability. Basically, we can get an atom based free energy contribution that can be summed into a score that we call LGFE, ligand grid free energy. This LGFE score is an estimate of binding free energy of the ligand in that pose. Because the frag maps are pre-computed, this simple assignment and summation is instantaneous and becomes the core of this technology as we move forward. The SILCS technology is not limited to overlaying ligands onto frag maps. We can also subject the ligand to the conformational sampling using what we call SILCS Monte Carlo or SILCS MC docking. In MC docking, we sample the translational, rotational, and torsional degrees of freedom of the ligand in the field of frag maps. The Metropolis criteria uses intramolecular energy of the ligand conformation and the LGFE to optimize the function of finding the best ligand pose and most favorable LGFE score. We can do this in a full docking mode where we are sampling the full rotational and translational space of the ligand in, say, a binding pocket, or in a mode we call pose refinement, which is more local relaxation from a known starting conformation, such as from a core crystal structure. The full docking takes typically an order of approximately 1 minute or so. So representing a speed up of over 1,000-fold compared to traditional free energy calculations. Here are results from a recent validation study that compares the free energy perturbation methodology with SILCS method. We have presented a comprehensive study of approximately 200 ligands across 8 different targets where we compared SILCS with number of previously published FEP studies. It is very evident that LGFE scores provide highly comparable relative binding affinity to the free energy perturbation calculated delta G values. And when using iteratively with experimental data, and this experimental data can be for small number of compounds as small as 10 molecules, we were able to improve the relative ranking of the ligand affinities shown by the percent correct data here on the right column, where for standard silks the percent correct was 0.71. With silks MC machine learning optimized approach, we can get it up to 0.81, which is on par and above the standard free energy perturbation methods that are out there. To summarize the key advantages of SILCS bio approach, it is the pre-computed GFE frag maps, allowing rapid and accurate ligand binding affinity estimates in a way that leads drug design process. And beyond the quantitative predictions, usually the frag maps easily allow for an understanding of types of functional groups that can be added to a molecule to increase its binding affinity, which is very useful in the medicinal chemistry to give ideas about synthetically accessible molecules. We note that frag maps explicitly count for protein flexibility. This is important because we know the protein can undergo local conformational changes in presence of different ligands. The frag maps account for desolvation effects, and this refers to the normalization procedure, which we described earlier. In addition to globular proteins, we also support membrane proteins such as GPCRs, ion channels, and transporters. We also have a specifically optimized protocol to apply the same method to RNA targets.
Now that we have the basic understanding of SILCS technology, let's take a quick look at the architecture of the SILCS Bio software suites that meet your needs. SILCS Bio offers 4 different suites. The small molecule suite applies the novel SILCS methodology to cover the conventional drug discovery process and includes SILCS frag maps, SILCS hotspots, SILCS farm, SILCS MC docking plus ligand optimization, and the SILCS BML programs. The biologics suite combines SILCS frag maps, SILCS hotspots, and the SILCS PPI in a single tool to build models for biologics formulations, which aim to reduce the protein-protein interaction and the aggregation, and the improving viscosity and the stability, among others. The SSFEP suite applies single-step free energy perturbation to deliver free energy calculations orders of magnitude faster than conventional FEP. This enables the evaluation of large numbers of modifications to a parent ligand while maintaining accuracy. The CGNFF suite contains the well-known CGNFF program to rapidly assign charm general force field topologies and the parameters for novel compounds. The CGNFF suite also contains CGNFF covalent for compounds covalently bound to proteins and a module for conventional MD simulations. All of these suites have been integrated into SILCS Bio graphical user interface. In the small molecule suite, like the traditional computer-aided drug design process, an input structure is required. This structure can be experimentally determined from crystallography, NMR, or cryo-EM. You can also use homogeneous modeling or AlphaFold to predict the initial structure. This initial starting structure is used as input to SILCS simulations which generate the SILCS frag maps. These frag maps are the basis for the rest of the small molecule suite. With SILCS hotspots, you can identify any allosteric binding site or adjacent site if you know where the ligand binds. If you don't know where the binding site is, you can choose the top-ranked binding site to start. With SILCS Farm, you can convert the SILCS frag maps at the given site into truly target-based pharmacophore features and virtually screen a prepared 3D compound library based on the features. With a known or putative binding site, you can use SILCS-MC to perform ligand docking and post-refinement. After the experimental testing with SILCS-BML, you can build Bayesian machine learning models to refine the SILCS frag maps weights based on the experimental data for further ligand optimization. To set up the SILCS simulations, you can choose the SILCS Bio GUI to easily click through the process with a connected HPC server by SSH protocol. Or you can use a command line interface with more advanced options on the server. Both GUI and the command line interface support multiple target types from globular proteins, membrane proteins, to RNAs. Once the SILCS simulations have been completed, you can visualize the SILCS frag maps using SILCS Bio GUI along with the target structure in different representations. These frag maps are useful not only for qualitative analysis, but also for quantitative analysis. Here is an APO structure of the tRNA methyltransferase and its corresponding SILCS frag maps. Overlaying the structure of a known ligand shows that the SILCS simulation successfully generated the hydrogen acceptor map around the oxygen atom and the hydrogen donor map around the nitrogen atom without the presence of the ligand. We can use the atomic GFE values to see the contributions of each atom of the ligand and inform further ligand optimization. Adding a benzene group to fill in the apolar map shows that the GFE of each carbon atom contributes to improve the binding affinity. SILCS hotspots can identify the binding pockets, including allosteric binding sites. In SILCS hotspots, a fragment database is docked in and around the protein to identify the potential binding sites. You can use your in-house fragment databases to detect the binding sites that have more desired features, and you can also use the FDA-approved compounds to validate the drug-like binding site. The SILCS Bio GUI provides a convenient way to perform SILCS hotspots and visualize the results. SILCS Farm can accurately generate the target-based pharmacophore features based on the SILCS frag maps at the chosen binding site. The pharmacophore generation is ultra-fast, which only takes a few seconds on a personal computer. You can manually select and deselect the features and adjust the radius for certain features as needed. The exclusion map, shown as small beads, can also be included for a pharmacophore-based virtual screening. The pharmacophore feature-based virtual screening included in the SILCS Bio platform can easily handle millions to billions of compounds. Finally, in SILCS-MC, you can perform ligand post-refinement, exhaustive docking, or ligand optimization. All docked poses or ligand modifications will be ranked by LGFE, and the atomic GFE contributions of each ligand will be available for visualization. With the subtle atomistic GFE contributions in your hands, you can either do a quick pose refinement to generate a more fit pose, or further refine the ligand using SILCS-MC ligand optimization. The accuracy of SILCS-MC is at the same level as traditional FEP methodology, but only in a fraction of the computing time. The SILCS BioGrid enables you to perform SILCS-MC ligand optimization with just a couple clicks. All you need to do is click on the add-on to modify, choose all groups you wish to apply, and then run the post-refinement for the newly generated ligands with delta LGFE values for all poses. After the runs are complete, modifications leading to favorable and unfavorable delta LGFE will be represented in orange and blue bars respectively. And you will be able to click on each modification and the add-ons of interest to see the atomic GFEs and get a quick summation from the ligand analysis panel. Now let's dig into the new updates coming in version 2025. Major updates in version 2025 feature many improvements to the command line interface, including the ability for users to customize their SILCS simulations with restraint modes, cofactors, and the different bilayer membranes, refined SILCS hotspots with machine learning, enhancements to MC docking for easier analysis of docked poses, and the ability to simultaneously dock multiple ligands, including waters, and the tools for analyzing the effects of modifications in ligand optimization. And thanks to the continuous feedbacks from our users, the graphical user interface in version 2025 includes multiple upgrades for a more intuitive experience, featuring the ability to export and import completed projects. Now let's take a detailed look at the improvements to the SILCS simulations in the command line interface. SILCS simulations, by default, invoke weak harmonic restraints on all C-alpha atoms during the MD portion of the simulations. These weak restraints allow local dynamics of up to roughly 2.5 angstrom backbone RMSD while preserving the overall structure of the target and allowing the collection of soil sampling probabilities. The default restraints setting has proven useful in the identification of hotspots, modeling of pharmacophore, and the docking of diverse compounds to the same set of frag maps. Depending on the stage of a drug design campaign, however, users may desire different restraint settings. For example, in the case that the multiple crystal structures are available of a target bound to a similar compounds, generating frag maps from SILCS simulations with increased restraints may be beneficial for docking studies of slightly modified ligands for which poses are highly anticipated to be consistent with those of their precursors. On the other hand, if users wish to allow only certain regions of protein to be restrained, the custom choice is available. Here is an example in which stronger restraints with a rigid restraint mode improve the predictive ability of SILCS-MC docking and the resulting LGFEs. Now, for general use, we advise users to remove all ligands, additional solvents, and waters from the input structure of your target for SILCS simulations, with some metal ions permitted to be retained. However, certain cases require the retention of specific ligands or cofactors, especially if they are crucial for blocking certain binding sites. Previously, SILCS simulations only supported the inclusion of a single ligand molecule via the command line. With version 2025, users can now add multiple ligands or cofactors to their SILCS simulations. Users with access to the CGNFF suite have an added benefit of the ability to retain covalently bound ligands with SILCS simulations, allowing the linking amino acid to undergo dynamics and capturing accurate interactions. in addition to customizable restraints and ability to include ligands and cofactors to our SILCS simulations. We've also expanded the SILCS membrane simulations to include pre-prepared bilayers. Previously, SILCS only supported bilayer membranes of 9:1 POPC to cholesterol ratios. Now, users can choose between 4 bilayer compositions of different POPC to cholesterol ratios, or users may also use their own custom bilayers. Finally, the SILCS technology has primarily focused on understanding the affinity patterns of solutes from the 1 microsecond trajectory, with frag maps generated for each solute atom type like benzene carbon and so on. In version 2025, we expand the analysis to include a detailed look at the sampling of the target protein itself during the same 1 microsecond trajectory to extract information about the side chain sampling. While a preliminary version of protein side chain sampling has been available for the protein-protein interaction module, available to biologic suite users, we are now refined the SILCS capabilities to fully leverage the potential of protein side chain sampling, allowing users to visualize and understand the behavior of their target.
Now let's take a detailed look at the SILCS-MC upgrades. Previously, when a user wished to run a SILCS-MC pose refinement, the input ligand had to be in the correct position and orientation prior to the calculation. In the 2025 version, if the user has a reference structure, all ligands to be docked can be aligned to the reference structure prior to the docking with the inclusion of only one additional parameter. Once SILCS-MC calculations are completed, users can now also examine each output ligand pose RMSD with respect to its input pose by setting the lig RMSD option to true. Additionally, the ligand center of mass difference from the input pose will also be output. Additionally, previously output poses of the same ligand were only extracted based on LGFE, leading to similar poses of the same ligand when more than one pose of the ligand was extracted. Now users can cluster their poses by RMSD when extracting more than one pose per ligand, removing redundant results and ensuring unique poses for further analysis. SILCS-MC docking can also now be customized with user-defined restraints on specific atoms. By using SILCS-MC restrain mode and supplying the indices of atoms to be restrained, users can preserve specific interactions of a portion of the ligand, while exploring conformations in the unrestrained portion of the ligand. Finally, we are also introducing the ability to simultaneously dock multiple ligands to a binding site in the same SILCS-MC docking run. By setting the sec-lig parameter to true and including the secondary ligand-specific parameters, users can dock 2 or more ligands with the primary ligand by default docked in a smaller search radius and the secondary ligand exploring poses around the primary ligand in a larger search radius simultaneously. By default, the secondary ligands are 15 water molecules, allowing users to predict and analyze water-mediated interactions. SILCS-MC docking with explicit waters can be particularly useful in cases where water-mediated interactions are crucial for a ligand's binding. Here we can see the improvement in pose prediction when accounting for water molecules. To the right, we use standard SILCS-MC docking, resulting in an RMSD of 6.5 angstroms and a deviation in center of geometry of 3.6 angstroms compared to the crystal resolved pose. With SILCS water, the predicted pose is significantly improved, with an RMSD and deviation in center geometry of only 1.1 angstroms with respect to the crystal resolved pose. Note that this RMSD is well within the motions we would expect to see if we were to simulate the crystal resolved pose with molecular dynamics. For more details, the early versions of SILCS-MC docking with water molecules as secondary ligands is presented in our recent publication in JCTC, as well as our webinar linked in the QR code. In these works, we show how the inclusion of water molecules can improve both the pose and affinity prediction of SILCS-MC docking. In version 2025, we also introduced the ligand optimization database. In the ligand optimization database, users can conveniently visualize ligand modifications in the context of how they affect the pose and affinity of the parent common substructure and how their different substructures compare in affinity. To generate the database, users simply need to run one command after running the SILCS-MC ligand optimization project, and the resulting CSV file can be loaded in any cheminformatics software such as MOE, as we're showing here, MolSoft, to view and analyze the parent substructure and ligand modifications with changes in LGFE and RMSD listed for the parent substructure and changes in LGFE listed for the modified site. Now let's review our improvement to SILCS hotspots. Previously, our hotspots calculations relied on further analysis and user intuition to narrow down which hotspots were promising binding sites. In version 2025, users can now use machine learning to re-rank SILCS hotspots results and identify the most druggable sites by simply setting the ML ranking parameter to true in the final step of the SILCS hotspots workflow. And since the ML ranking is done at the end of the workflow, users with SILCS hotspots results from previous versions of SILCS software can use their previous results as input without running new hotspots calculations to take advantage of the machine learning-based ranking. Here's a closer look at the SILCS hotspots with machine learning ranking. On the left, we have our SILCS simulation or SILCS hotspots ranked by LGFE, as was previously done as default, with the blue indicating less favorable average LGFE scores and red indicating favorable LGFE scores. In the middle, we have our ML ranked SILCS hotspots, which is now the default in version 2025, with red indicating druggable sites. Turning the structure of the KRAS protein, we can see that the crystal resolved ligand is located where two high-ranked druggable hotspots are predicted. More information can be found in our 2024 JCIM paper here. Now let's touch on the major update to the graphical user interface. The SILCS Bio GUI is free to download. However, sharing projects remained a limitation until now. In the 2025 version, users can export a project by simply clicking a button. They can choose their project name, save it, and this will package all the necessary data into a convenient file. Once the project is successfully exported, the user can send the package to another user. This user can then go to the corresponding Continue Project window and click Import Project. Then select the SILCS Bio project file and hit Enter. Once the project is imported, the user can click the imported project and then view the data as if they ran the project themselves.
Next, we will share a case study that demonstrates the applicability of small molecule suite in a structure-based drug design workflow. In this retrospective case study, we tested the ability of our new ML-ranked SILCS hotspots and SILCS-MC docking on a ligand optimization campaign reported in a recent study in the Journal of Medicinal Chemistry with KRAS and non-covalent inhibitors. While the non-covalent inhibitor was published with the crystal structure, we used previously published APO structures of KRAS to evaluate our SILCS hotspots predictions. Here is our setup for our SILCS simulations. Note here that we have taken advantage of our SILCS simulation upgrade and kept the GTP as the cofactor. After the SILCS simulations are complete, we can see that the anticipated binding site opens up compared to the crystal structure, allowing the solutes to sample the site and result in favorable affinity patterns. We then ran SILCS hotspots with machine learning ranking. Overlaying the crystal resolved ligand shows that the correct binding site is identified as top rank site, highlighting the ability of SILCS hotspots to predict druggable sites. Okay. With the ability of SILCS hotspots to identify the druggable site validated, we then applied different SILCS MC modes to evaluate its ability to dock ligands on the hollow structure. Compared to rigid scoring with pose evaluation, pose refinement allows for slight changes from the crystal pose, resulting in local minimum LGFEs that are comparable to experimental affinity. However, here we can see that SILCS MC docking with the ligand able to fully explore the binding pocket is able to best reproduce the experimental affinity of the inhibitor. We then constructed all ligands from the medicinal chemistry campaign to test the predictability of SILCS MC docking and resulting LGFEs. Applying SILCS MC docking, we can see that we have a reasonable correlation with the experimental affinities. With SILCS technology, we can analyze the energetic contributions of specific functional groups of a ligand. Taking an in-depth look at specific R group modifications from the campaign shows that while modifications at R7 are not well captured, we see promising correlations and ranking for both R4 and R2 congeneric series. Here we can see the true value of SILCS MC docking with the ability to extract atom or group-wise contributions to the affinity of the docked ligand. Here we are showing three compounds from each R group position that modifications drive changes in overall affinity with minimal impact on the remainder of the ligand. Notably, the trend is consistent with experimental data. This analysis is made simpler with our new ligand optimization database tool. So how long did this SILCS SM campaign take? Again, the true value of SILCS comes from one upfront pre-computation of SILCS frag maps, enabling rapid prediction of hotspots and evaluation of multitudes of ligands taking only seconds to minutes. And that sums up the additions to the SILCS universe. Please sign up for our newsletter to hear about our future additions to the SILCS software suites, which will include SILCS Covalent for irreversible inhibitor optimization, SILCS H-ERG blockade for rapid prediction of ligand binding to H-ERG channels, SILCS permeability for rapid prediction of ligand passive permeability, SILCS kinetics for rapid prediction of ligand dissociation kinetics, and lastly, a major update to CGEN-FF with 1400 new compounds being added to the training set. Overall, our future goals are focused on combining the SILCS physics-based frag maps with AI technologies to streamline the drug design and discovery process. Thank you for tuning in. We are excited to bring you version 2025 of our software suites with improved performance and new functionalities. For more details on our new features, please visit docs.silksbio.com. And for general inquiries, please visit us at www.silksbio.com. And we are happy to take any questions now.
All right. So let's see. Yeah, we have a question. What is the cutoff for RMST clustering used in the option RMST clustering?
Yeah. So we were doing the clustering and it's a leader-based clustering. So we first sort our poses by LGFB. And then starting from the best one, we cluster. So if you have n pose equals 1, it's always going to be the same first pose, no matter how many poses you extract.
Is the GUI export import feature available for all suites?
Yes. So the export import feature is available in all the suites in the GUI. So you are very welcome to share the GUI with your medicinal chemist or biologist or other coworkers.
How does the ML ranked hotspots compare to other methods like sitemap?
Yeah, so I guess other conventional methods generally use a crystal structure. So you're locked into the one structure that you're using, whereas SILCS incorporates the ensemble of structures from the simulations. So let's say your crystal structure has an included binding site. Methods that only use the one structure are not going to be able to identify hotspots in that site, whereas with SILCS hotspots, since we're using that ensemble of structures, the occluded binding site can open up, and then the SILCS hotspots methodology can identify this, the hotspot.
Is there a specification limitation on what custom bilayer PDP is used, minimum size?
So in the SILCS membrane setup, the minimum size of the bilayer membrane, which is the default, is 120 angstrom by 120 angstrom. And the maximum size of the bilayer membrane is 200 by 200. So if your system exceeds the maximum size, you can always apply your own membrane template in the SILCS membrane setup stage. Just to make sure the size of the membrane can cover the protein, and you can always visualize the protein membrane system after the SILCS membrane setup.
Okay. Next one. Are any restraints applied to the ligand cofactor or covalent ligand in the SILCS simulations?
Yeah, so in the SILCS simulations, there's going to be light, weak restraints on the heavy atoms of the ligand, and they're going to be similar to the C alpha atoms of the protein, so about 50 kilojoules per mole angstrom.
Yeah, and then because you have those restraints, that part of the map is covered by exclusion map, which blocks the other ligands from docking there. So yes. Does the reference ligand for the pose alignment in SILCS MC docking need to be same ligand, or can it be any ligand in the binding pocket?
So theoretically, the reference ligand should be similar to the ligands for docking. And the reference ligand can be the parent ligand or the common structure of your ligands. The key point is we use a reference structure to give the other ligands a good initial orientation and the starting position, and to further refine the poses of the structures.
Right. Then do you assess cases where ligand binding induces significant protein dynamics, and can accuracy be improved with unrestrained dynamics?
So in the case where a protein is undergoing significant conformational changes, you'll want to do separate SILCS simulations. The reason we don't want to do a completely unrestrained dynamics is that your probability maps are going to be washed out, and you're not going to be able to get proper frag maps from it. So a solution to that is maybe do an MD of your protein, identify the conformations that you're expecting, then extract those distinct conformations and submit your separate SILCS simulations.
Then we have, thank you for the nice presentation. My question is about new ML ranking hotspots. Has it been tested for sites that are open to the lipid bilayer, or is it recommended only for sites that are more traditional drug binding sites? And regarding the decision function values, are there guidelines for the range of values to look at? Thank you. Yeah, go ahead, Alex.
The method is not optimized for lipid proteins on the surface. However, the standard hotspots will be mapping out those regions. So the new ML hotspots are focused more on globular proteins and then the interiors of GPCRs and so on. But the standard hotspots will give you a lot of information about regions where ligands will bind at the interface between the protein and the surface. And then the ML ranking function, it is a rank ordered function that can be used to sort of select primary sites. However, it is a like any other ML function, it's not ideal. So some known binding sites do rank below like the standard cutoff of 0 that we present. So what's nice about the SILCS GUI is it allows for these other sites that rank a little bit lower to be readily visualized. So you can take a look at those and maybe follow up of those with some additional like docking of some FDA approved compounds and so on.
All right. I think that's all in the riddle. Someone is raising the hand, so maybe we can allow them to talk. Kalnya Dubinina, if you can talk.
Okay. Hi, everybody. I have a question. Unfortunately, I missed first part of your presentation, so maybe address my questions before. Is there any limitation of data set of compounds, for virtual screening like docking? I understand that it could be different parameters more, but any timeline, can you handle with million, billion, or trillion of compounds, and how long it takes? Let's say the simplest setup of docking parameters and virtual screening.
Yeah, that's a great question. So how typically we handle, if you are going into millions and billions, then we try to go through a different route in the small molecule approach where use the frag maps to first, generate pharmacophore features. So that is purely target-based pharmacophore feature that you generate from the frag maps, and then you can do a pharmacophore screening of your, billion compounds and come to, let's say, a few thousand, few 100,000, which are, then you're going to have them already in a reasonable pocket that are, filtered through the pharmacophore models. And then we can use the post-refinement tool to quickly score them with little bit refinement. And then we can sort them, using our LGFE scores. So that's how we bypass, instead of purely docking each and every molecule into the pocket, we can, screen the billions and millions first through the pharmacophore screening and then do the ranking by LGFE.
Also,
sorry.
Also, I do want to emphasize that our SILCS Bio software is not limited by any form of tokens. So as long as you have enough computational resource, you're very welcome to dock a very large database.
Mm-hmm. And for fragment-based design, like you say it's a few 100,000 kind of limit, right? What's the kind of limit there?
There's no limit. I mean, it's a matter of
limit.
CPU time. I mean, the CGNFF force field coverage is very, very large, so that'll take care of that. And then, it's like what Oliver was referring to. You can set jobs up on multiple GPUs, so the sky's the limit. It's it's not absolutely instantaneous, and the pose refinement is very quick. I mean, less than a second, and even the full docking is quite fast. So the limit is up to the customer. So tens, hundreds, million compounds. That's whatever you're interested in.
Okay, thank you.
Okay, thank you. I think that's all the questions. So I'd like to thank everyone for joining again. And if you have any other questions, do send us an email at info@silcsbio.com, and we are happy to answer any questions. And the recording for this session will be also available. So if you want to share that with anyone, please do. And yeah, thank you. Thank you, Alex, and thank you everyone for being here. Have a good day.